Hi everyone, I'm Adam, responsible for open source at OpenBNB. Since we have recently open sourced a new multimodal named MiniCPM-V 2.6, which has achieved very good results. So I'm here today to talk about how to fine-tune this model, that is to perform SFT. First, we need to copy the code from our official GitHub repository to our local machine. The command to copy the code has been provided in the tutorial. So all you need to do is copy this one-line command, then paste it into the desired location. For example, I'm copying this code to the MiniCPM-V 2.6 folder, so just enter the copied command in this path. At this point, the code will start downloading. After a short wait, the code will be downloaded. We can see that there is no file in the MiniCPM-V 2.6 folder, which means there's no official code for MiniCPM-V. Next, we will go into the folder where the code was downloaded. We'll go into the main folder where the code was downloaded. Then we will find the file named requirements.txt. We need to run pip install -r on the requirement in this file. Then we have the requirements file. Okay, great. Once we enter this, we'll start the installation process. We need to install the necessary packages. On my side, I already installed them, so I will skip this part. Once you've installed all the dependencies, we can proceed with modifying the training script. Next, let's take a look at the training script. In the fine-tune folder, where the code was downloaded, there's a folder named fine-tune. Inside this folder, there's the file called fine-tune. There's also a shared file called fine-tune LoRA and a shared file for the full model. Let's open these files and take a look. First, we will look at the full fine-tune settings. There's a shell file for DS. We need to explain some of these parameters. The parameter at the top are mainly for setting up your local environment. How many different GPUs you have on each machine and how many machines you're using. This is a node parameter. There are these two communication address. The important part comes next. This is the model parameter. This parameter needs to be modified. We need to modify this one. We can change it to the local path of our model. We've already downloaded the model using the method mentioned earlier. For example, our model is saved at this path on the local machine. So in the model input, we enter the local MiniCPM 2.6 path. Next, we need to input our data. This includes two, one for machine and one for validation during training. Next, we have the LLM type. Input Queen 2. Because the version we are using is 2.6, we need to input Queen 2. Because different kind of models can use different kinds of data processing. Great. The next two lines are code for machines that use different communication method. If your machine doesn't support the two method, you can enter a simple check rule. For example, if you have A100 or H100, you can skip these two lines of code as they are for faster communication. Okay, the next parameter we need to pay attention to are these. These are BF16 and BF16 full parameters. I will give some instructions. For example, BF16, if it is equals to true, it means we are using BF16 data precision for training. Below that FP16 now will be false. That is BF16 and FP16. We can use one at a time. A simple rule of thumb is if your machine is like 4090 or A100 or H100, we can use FP16 for training. Okay, great. Let's jump to the next part. Take a look at these parameters. They are quite important too. Regarding tune vision, is about whether we train the image module in a multimodal module. If it's true, then it indicates that we need to train the image module in the model. Below we can see tune LLM. If we write it false, it means that we are not training the language module. The specific trade-off can be based on everyone's available video memory. Because we adjust more modules for our training, we will actually use more video memory. This is closely related to our machines. Alright, let's take another look at the following section. Model max length refers to the maximum input size of our model, which usually is set to 2048 by default. Of course, we need to adjust this parameter based on our data and the video memory size of our hardware. Generally speaking, the larger the parameter is, the more video memory it will consume. So this can be based on our data and as well as the size of the video memory. Moving on, this parameter is the maximum step, indicates the maximum number of steps we will train. Equal step indicates how often we perform validation during training. Okay, the next two parameter, log due and output due, refers to the directories which our log file and the final model will be saved. They determine which folder these files will be placed in. Next, we will see the batch size. How many batch size we use for training for one graphic cards, the batch size will directly and significantly affect our video memory. The larger this number is, the more video memory it will occupy. Secondly, each graphic cards, we perform validation for each batch size. Each validation will also consume a significant amount of video memory during the validation process. Therefore, I suggest that everyone should, based on their decision on their own video memory capacity. If there's sufficient memory, we should prioritize increasing the batch size. Another parameter is the gradient accumulation. If we have limited video memory but still want to achieve the effect of larger batch size, then you can increase this parameter a bit. For example, we can set it to 8 or 32. When you don't have enough video memory, this parameter become very useful. We need to talk about these parameters for saving our model. The step here refers to the strategy we need to follow for saving the model. These are mainly two strategies for this. One is for saving after each epoch, and the other is for saving after a certain number of training steps. We have chosen step here, which means we save the model after every 1000 training steps. If you want to save each after epoch instead, you should write epoch and change it to port. The next is learning rate. The default learning rate is a to the minus 6. If you find that the model's loss is decreasing slowly or the loss is oscillating severely, we should consider adjusting the learning rate first. The last few important parameters are these two. First, the gradient checking point. I was just enabling this by default. If you have a very powerful machine, you might not need to consider enabling this. Otherwise, I still recommend enabling the gradient checking point feature. It can significantly reduce your radio memory usage. The last parameter that need to explain is this one, is DS configure. This actually means that it's using 02 for training. If you are running out of video memory, you might consider switching to 03. 03 has higher communication cost, so we still recommend using 02 first. If 02 is not working, we can consider using 03. That concludes the parameter for a batch style script. Next, I will introduce how the dataset is set up. As we have usually discussed, let's take a look at how the dataset is set up. In fact, what we need to do is to check these two in their respective position. This is here. We can see data in Evo data are essentially the same format. So we only need to look at one of them. A basic principle is that we can validate the data set. We should take a look at format of the validation data set. Let's open it. So first is a JSON file, and inside the JSON file is a list, and the list contains multiple data items. Let's take one data. Lastly, we need to give it an ID value. This ID value, please note, should not be repeated, which means the number following the ID should be unique. The second is that we should have an image field. The image field is followed by the address of image corresponding to this data item. We should write the absolute path here. The third is the conversations. The conversations field is a list. This list can store multiple rounds of dialogue. For example, let's take a look at the first sentence is a content. A sentence can actually be seen as another field called user, which means the sentence is a question from the user issued by us. Here we need to pay attention to the sentence, except for your question. The first thing to do is to enter image symbol. At the beginning of the first person question, an image symbol is required. This image symbol represents that this data item contains an image. This is our good. Next we can see the second dictionary has a row field. Its row is written as assistant. It represents the model's output. Since we are training here, so this should be the expected output of the model. What we expect the model to output. Statement then that the model learns. So the content field behind is we need to learn a field, of course. Since this is single round dialogue, if it's a multi-round dialogue, actually we can continue to construct according to this format. We can continue to construct it. So the two dictionaries we mentioned earlier are the human questions and the model's answer in the first round of dialogue. If it's multi-round dialogue, we just need to continue to add human and an alternative response according to the same format. So we can construct multiple rounds of dialogue for this model. Here we need to note that in a human conversation, only the first round required us to pass an image, otherwise it can be omitted. The first one is mandatory. The construction of the dataset is finished. We've just talked about how to construct it. Then this JSON file is a list. The list contains multiple dictionary like one we mentioned earlier. Each dictionary is a data item. After the dataset and the parameters in the shell script are set, we can start training. Training will first turn to one we just saw downloaded. We go to fine-tune address on GitHub's code. Go to the fine-tune address. Good. At the time we run a shell script, we have set up first save the shell script. Then it will start loading the model. We can see as time goes by, it starts training. It may take a little time. Using the 0-2 method for training, its speed is a bit faster. So let's wait for a while, because it takes some time. So I will stop here and wait. Great, the training is completed. Let's take a look at the final result. The results are actually saved in the folder we set for saving, which is called the output dir. This is output directory we configured. Here I have conducted 10 rounds of training. After training, the model is saved under checkpoint 10. This contains the full fine-tuning. So here we saved all the fine-tuned parameters. Because it occupies a lot of memory, I will delete it first. Next, we will start the LoRA inversion process, which is how we set the LoRA parameters. In fact, the LoRA parameters are mostly the same as the full fine-tuning, except for the different parts. The different parts, firstly, you need to pay attention to the KV modules in the language model, such as these, which are the modules of the language model. I don't recommend modifying these modules when we're using LoRA. We need to pay attention to when we're using LoRA. Firstly, the tune LLM here must be false, because we are fine-tuning the language model's KV model. So the original weight of the language model should be turned off. Secondly, we must set a US LoRA V2. That is, when we command exist, it will perform LoRA fine-tuning. The rest is most the same as full fine-tuning. The two visions which can be turned on or off depending on your memory and needs. I won't go into more details and continue training. So we are back to the fine-tune folder. That is the fine-tune folder. We can see that this address is in the fine-tune folder. Then enter byte. Now we'll run a bash script for Great, here is starting to load the model. I will pause here. It takes a little bit of time, so we just need and with some patience. After it output the result. Okay, I'm back everyone. Then we can see that after I trained for 5 steps, due to time constraint, I only trained for 5 steps. Then it saved to our LoRA. The adapter module of LoRA has already been saved. After saving, what we need to do is actually merge. That is because the LoRA actually trains some enhanced module, which means it only has a patch-like module inside. So we need to combine this patch with the original module. The code for this is we need to merge the patch with the original module to get a new model. Let's test this code. This code I will explain to you. There are some important points that you need to change in this code, which are these addresses. You only need to change these three. The first is model type. This model type actually says where your original model is located. That is when the MiniCPM-V 2.6 is stored after training. It's stored at which address? And the second is checkpoint, which is the address of your build training. Inside is checkpoint-V, right? Then we copy this address, which is the checkpoint-V address, and pasted it, which is the address when you save to LoRA with the original module. This is customized. You can write it everywhere. Okay, run it again, but it will take some time, so I will pause again. Okay, it has run successfully. Let's take a look. We have obtained a new module in the folder we set. This new module is a full model. Its architecture and parameter size are the same as the original MiniCPM-V 2.6. This is how we merge LoRA into the original model and save it. The code for merging LoRA is in the tutorial. So that's all for today's instruction. Happy coding everyone. Don't forget to follow us.